So we're going to do a little review. Some of it's going to be for EOC and some of them going to be for the current unit, but it was just a good way to put a couple things together. So we're going to go with exponents first. And this is hopefully all review, and we've been doing some of it even as we were factoring and multiplying. So hopefully you remember some of these things. I would love it if you would want to turn off your, not turn it off, but pause your video right now and see if you can fill in any of these on your own. I think there's a lot of them you could. It'd be kind of a fun challenge, so I'd encourage you to do that. So what we're talking about here is we're just going to go through and I'll do some examples off to the side so that it will kind of help you remember too. When you combine like terms, so if I take 4x plus 7x, I get 11x, yes? So when you combine like terms, the exponents don't change. So 4x plus 7x is 11x. See how that exponent does not change. When you multiply like bases, so if I take 4x times 7x, okay, I get 28x squared, because when I multiply like bases, you add the exponents. When you divide like bases, you've probably seen it by now. I can't use 4 and 7 on this one's not as easy, okay? But let's say if I'm going to divide like bases, if I have x to the 10th over x to the 3rd, when I divide, I get x to the 7th. So I'm going to subtract my exponents. When you have a power to a power, so this is saying if I have x to the 3rd to the 7th. When I take a power to a power, what do I do with my exponents? I get x to the 21st, right? Because I multiply the exponents. Now, if there's a product of a power, for instance, and I give you a little example here. If I'm going to multiply that, what's going to happen is I take everything to that power. So I have 3 to the 2nd, x to the 2nd, y to the... So I've just talked about power to a power. I'm going to multiply the exponent, so that's y to the 8th. So this would give me, so I have a little more space, you would see that you get 9, x to the 2nd, y to the 8th. So if there's a product of a power, then each term, not term, because that's a term. Each individual, each thing, you know what, we're not even going to be, each thing, whether it's a variable or a number, is taken to a power. Okay, so each individual, so the number goes to a power, the variable goes to a power, and if I have a power on the inside and the outside, I'm going to multiply. Any non-zero number to the power of 0 is 1. So 12 to the 0 power, that's equal to 1. X to the 0 power, that's equal to 1. Okay? X to the 2nd, y to the 3rd to the 0 power, that's equal to 1. Okay? If there is a negative exponent, I have 2 lines here because there's 2 ways you can think of it. If there is a negative exponent, it takes it to its opposite place. And what I mean by that is numerator to denominator or denominator to numerator. Okay, it goes to its opposite place. That's how I usually say it. It goes to its opposite place. The other thing you can remember with it, if I can just flip where it's at. So I can flip it. And so it goes to its opposite place, but I could also flip it. So if I have x to the negative 5th, that's 1 over x to the 5th. But also if I have x to the 2nd, y to the 3rd, all of it to the negative 4, the whole thing can flip over. And then I have power of a product, so everything goes to that power. So I have y to the 12th over x to the 8th. Okay, just to give you a little bit of that. And on the back of this sheet, you have all of these problems. Let's just look at a couple of them and see what happens on them and what we're going to do as far as simplifying and everything like that. So I just picked a couple we're going to do. So here, we're going to multiply. Now notice the coefficients, they don't change. That's just 4 times 2, that's 8. I have two ways I can do it with the variable. Okay, so the 4 times 2 is 8. With the variable, I have two ways to do it. One, I could take care of the negative exponents to begin with. So I could have 4 over r to the third times 2r squared. Then I could get 8 r to the second over r to the third. And what I like to do with this is the 8 is just going to hang out. With the variables, I like to see where it is bigger, and then that's where I send it. So see how the 8 just stays where it's at. The r is bigger in the bottom. Remember, when I divide, I subtract. So 3 minus 2 is 1, but it's going to be in the bottom. So it'd be r to the second. The other way I could do this one is I could just multiply it as they are, and I get 8 r to the, when I multiply like bases, I add the exponent. So that'd be r to the negative 1. Well, if I ever have a negative exponent, it sends it to the bottom. The 8 doesn't move. It just has a positive exponent of 1. So it just stays there, but the r would go to the bottom. Both of these, notice how we get the same answer either way. So there's not like one right way to do it. You just have to figure out what does your brain see and go with that. Okay. Next one I wanted to do was number 9. And again, there's two ways that you could do it. One, I can just multiply everything straight across. So I'm just going to start off that way. And I get 12. A to the, I'm going to multiply a to the third times a to the negative 4. So I add my exponents, I get a negative 1. B to the 2 times negative 3, I also get a negative 1. So when I simplify this one, the 12 has an exponent of positive 1. It stays. But the a goes to the bottom, and the b does, and now that negative is gone. The other way I could do it is I could take care of the negative exponent first. So I have 4a to the third b squared times 3 over a to the fourth b to the third. Then what I can do from here, 4 times 3, that stays. Look at the a's. Where's it bigger, top or bottom? Bigger in the bottom. Then I take 4 minus 3, I get a. B, 3 minus 2, again bigger in the bottom. On this one right here, again, 2 options. I know you're probably sick of the options, but it really does just depend on what does your eye see. And if you want to, anytime during this, pause it, try it on your own and see if you're getting the same answer I'm getting. So the 3 has an exponent of 1, it stays. The m has an exponent of negative, so it's going to go to the bottom. M to the third is positive, it stays. So it doesn't necessarily move as in the bottom. It depends on if it has a positive or negative exponent. So then I can just multiply the bottom. When I multiply like bases, I add the exponents. 4 plus 3 is 7. Okay. Now some people's brains do it right here. Mine does not. I do not subtract negatives well. So I could go, well, 3 stays here. And then I could say I'm just going to take negative 4. Negative 4 minus 3, that's going to be a negative 7. So if I just go negative 4 minus 3, that's a negative 7. Then I take care of the negative exponent. So it's going to be 3 over m to the 7th. Okay. Now I want to look at 11 and 13 at the same time. The reason for that is because it totally depends on where that exponent of 0 is. Here my exponent is on the outside, so it doesn't matter what is on the inside. I could have something like 20 x to the 12th y to the 100th over x to the 17th y to the negative 2400. And if it was all to the 0, that would still be equal to 1, just like this is equal to 1. So it just depends on where that exponent is. But on this one, notice, what you're going to do here is you have to take everything to a power. So 4 goes to the 4th power. R goes from the 0 to the 4th. When I take a power to a power, I multiply, so that's going to be 0. So 4 to the 4th, 4 times 4 is 16 times 4 is 64. Or I can just go 16. Sorry, I'm just going to take 4 to the 4th. I don't have that one down. 4 to the 4th power. Okay, and the way I do a power, use this caret key to the 4th, gives me 256. R to the 0 power is 1, so that's my entire answer. Okay, let's look at number 27. So on number 27, we're going to just start simplifying. And the beauty of it is you get, like in this one, you get 4 problems in one. You have the coefficients, You have X, you have Y, you have Z. So you get to do 4 problems in one. It's cool. So if I were doing this one, the first thing I would do is I'd go through and I'd start moving things around and canceling. Notice I have a 4 on the top and the 4 on the bottom. Those cancel out, just like I would with fractions. I have an x to the 0. Well, that's 1, so that doesn't do anything. Y to the negative 2, when I have a negative exponent, it goes to its opposite place. It's in the numerator. It goes to the denominator. And then Z has a positive exponent. It just hangs out. It doesn't go too far. Okay? On number 29 was the next one I was going to do. On 29, okay, again, treat it like you have 1, 2, 3, 4 problems. So, 4 over 3, they don't cancel each other out. They just hang out. Can't do anything with them. Look at the m's. Where is it bigger, top or bottom? It's bigger in the top, so it's going to end up in the top. And now I just subtract, because when I divide, I subtract exponents. 4 minus 2 is 2. N to the third over n to the second, bigger in the top, so n stays up top. 3 minus 2 is 1. P, bigger in the bottom, so it goes to the bottom. And I'm going to subtract 4 minus 3. It goes to the bottom, so I can subtract up. 4 minus 3 is 1. That's my answer. Okay? Okay, let's go back to the notes and talk about roots. We're going to be using these roots in the next one of the sections we're going to be doing this week. So what I'd love for you to do is on this, turn off your, pause your video and go through and fill out all of your perfect squares. I'm going to do that same thing. So we're going to turn off and we're going to pause our video and we're going to fill in perfect squares. I'll start you off 1 squared, 2 squared. Okay, and if you have to use your calculator, that's okay. But we're going to go and fill those all out. So hopefully you got a lot of these. And how many have got all of them without a calculator? Okay, nice job. Now I added the 16. I added that, so don't worry about that. So if you can know you should definitely know your first 10. And I think it's helpful to know all the way up through 15. And like I showed you earlier, I didn't even remember 16 squared off the top of my head. But 16 squared is 256. And you can fill out more. I used to know more of them when I was a student in college. But I just don't think that we go too far anymore. And we all have calculators nowadays, so it's not a big deal. Perfect cubes. 1 cubed. 2 cubed. Cubed. 2 times 2 is 4 times 2 is 8. 3 cubed. 3 times 3 is 9 times 3 is 27. 4 cubed. 4 times 4 is 16 times 4 is 64. 5 cubed. 5 times 5 is 25. 25 times 5 is 125. And that's all I have also. Okay? So those are the only perfect cubes I have. Okay. So we're going to be using this. This is just helpful. And again, some of this, like this up here, that's more review for EOC. This is what we're going to be using, especially this over here when we go to solve by square roots, quadratics by square roots. So we're going to see that in about a day or so. Okay. How to simplify if not a perfect square. And I left this blank because it depends on how you've done it. I'm going to show you the way I did it, but there's many ways to do it. So what I use is I break into perfect square, non-perfect square. Okay. The other way you can do it is if you do prime factorization. So, factor tree. And I'll show both. See what you remember. Okay. So the first method that I use is I break it into perfect square, non-perfect square. So I want to find the largest perfect square that goes into 24. And you can find out that largest perfect square is 4. So I break it into, here's my perfect square. Okay, so when I say this, I break it into perfect square, perfect, non-perfect. Okay. This is the refrigerator, okay? This is where the leftovers are. So this is the fridge. Put the leftovers in there. So I have a perfect square of 4. What's left over? 6. What's the square root of 4? 2. Now, you always double check this just to make sure, just kind of like with reducing fractions, with factoring, anything. Look to see if there's anything that goes into it. Well, 2 and 3 are the only thing that go into it. Is 2 a perfect square? Is 3 a perfect square? No. So this is my answer. The other way I can do that is I can break it down using a factor tree. So a factor tree, I break it into two things that multiply. And just to show you, it doesn't matter what you pick. Pick any two numbers that multiply to 24. So I'm going to pick 3 and 8. 3 is prime, leave it alone. 8 goes into 4 and 2. 2 is prime, leave it alone. 2 goes into 2 and 2. Then what you want to do is you want to circle any that they're a pair. See how this is a pair? So I would circle that one. That one comes out. That one gives me 2. These are my leftovers. They get multiplied back together and go back in. Okay, look at 80. And again, I would love it if you would pause your video and try these on your own. Okay, 80. I can go perfect square, non-perfect square. So a perfect square that goes into it. I think 16 does, okay? But I'm going to show you that it doesn't have to be the largest one. So even if I broke this into 4 and 20. The reason I'm doing that is because I know those off the top of my head without using a calculator. This gives me 2. 20 can be broken down into perfect square and non-perfect square. So that 2 hangs out. Now I'm going to take the square root of 4, and I get 2. And this is always multiplication in through here. All of this is multiplication, so I get 4 square root 5. Now this one might have been faster to do by factor tree. So 80 breaks into 8 and 10. Go with the obvious things. 8 breaks into 4 and 2. 4 breaks into 2 and 2. 10 breaks into 2 and 5. Okay? Now once it's called a factor tree because these are the branches, these are the leaves. Once the leaf has been broken down, like this number, doesn't apply to us anymore. Now let's look at the pairs. See how this is a pair and this is a pair. So those two come out, so I get a 2 times 2. This is left over 5, so I get 4 square root 5. So those are the two different methods that I use on a frequent basis, okay? Try this next one on your own. Do whatever method. I'm going to do both methods, and we'll be back. So on 126, when I looked at this, I did not see the perfect square right away, so I actually went to the factor tree because I just started breaking it down as way faster. Whereas on this one, you know, I'd already done this, so I kind of knew what to use. On this one, I would have taken my calculator. If I'm using this method, take your calculator and just start going through perfect squares. I would have started with 4. 4 gave me a decimal. I mean, 4 did not. Yeah, 4 gave me a decimal, so I knew to try something else. So I just start going through my perfect squares if I'm not sure what to do if I'm going to be using this method. Okay, good. Now, I want you to look in your packet on the page that looks like this, Simplifying Radicals Classwork. And we've already kind of done some like these first ones. I want to jump down further to the bottom. So I'm going to jump down to number 9. And I want to show you if the number's on the outside, that just keeps on tagging along. So I'm going to do the method because 75, I already know a perfect square in there is 25. So I'm going to use that. So that 8 just hangs out. I break 75 into perfect square and non-perfect square. How many quarters? That's 3. So I have 8, take the square root of 5, that's 5 square root 3. Oops, can't do that. 5 times 8 is 40 square root 3. There's a radical. Okay? So don't forget that 8. If I'm doing factor tree, just be aware of that 8 and don't forget it. All the rest of them, you're going to be doing the same thing. So on this one right here, just because I live in the time of calculators, I would probably, and I have a number out in front, I'd leave that 8. I'd break this into 4. Actually, what I do is I would take 128, divide it by 4, and let's see if there's an, oh, and look, I get a 32. Okay, so what I did is I broke it down by 4, knowing that 4 was a perfect square. I got a 32. I know 32 is divisible by 4 and 8, so that means there's another 4 in there. So now what I'm going to do, that's 4 times 4. I'm going to go back, and I'm going to try 16, so then I can get my largest perfect square. And that gives me 8. That's even not my largest, but I'm going to start there. That's 16 and square root 8. 8 comes down. What? We're stuck on 8 today. Square root of 16 is 4. I can break 8 down into 4 and 2. So I just keep breaking them down into perfect squares until I have no more left. I don't have any more left, sorry. So this is 32 times 2 square root 2, because square root 4 is 2. That gives me 64 square root 2. Okay? So that means that I could have taken 16 to begin with. If I had gone with, oh, I did go with 16. And I could have gone one bigger, so 16 times 4. I could have used 64. Oh, duh, 64 goes in. So I could have used 64 to begin with. But it doesn't make any difference, so I would have had 8 times 8, which was 64. Notice we get to the answer either way. So, and you could have also done this by factor tree. Great. Okay, check with your teacher as to what your assignment is. If you have any questions, you know where to find us.